ndimtima umo tiende pamozi 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 ndimtima umo.
Hello, good morning, viewers, once again. Welcome to the MTN Telescope. My names are James Kabuye. Again, we are going to go through together Physics Paper 2, 2016. I hope that we'll be able to follow each other. We'll go straight into the questions. Question 9. The question reads, Figure 9.1 shows a section of a tire of a wheelbarrow. The tire exerts pressure on the ground. A. Pressure can be measured in Pascal. Part 1. What is a Pascal? I think the point here is to understand what a Pascal is, and very quickly, for us to say that pressure is equal to 1 Pascal, we must understand that this can only be possible if a force of 1 Newton acts per square meter. That is when 1 Pascal of pressure is attained. When pressure of 1 Newton acts per unit square meter. Part 2. The mass resting on a wheelbarrow tire is 60 kgs. The area of the tire in contact with the ground is 0.024 square meters. Calculate the pressure exerted on the ground. Dear viewers, let me just try and illustrate this by solving something here. Pressure is equal to force over area. That is the formula we must use. But we must understand that in the question we are told the mass of this, the mass that is resting on the wheelbarrow, which is 60 kgs. So we must convert 60 kgs to newtons. Weight is equal to mg. Where m is the mass and g is the gravitational force. So 60 kg times 10 will give us 600 newtons. That is the value we must use as the force. Once we have this value, then we can place it where F is and put the area where it is and find the pressure. 600 newtons divided by 0.0024, so that we get the pressure as 250,000 newtons per square meter. That is the pressure, which can be equal to 250,000 pascals. That is the answer to that question. As the wheelbarrow was being pushed, the tire went over a small stone. Describe and explain how the pressure changes. We must understand from the formula that pressure is equal to force over area. When the area is small and the force is constant, this force, then the pressure goes high. So the smaller the area, the greater the pressure. So you can see that that small stone is providing a very small surface area and therefore increases the pressure on the wheelbarrow tire. Part B, the temperature of the tire increased due to friction with the road and heat from the surroundings. Using the kinetic theory, explain what happens to the pressure inside the tire if the size of the tire does not change. If the size of the tire does not change, it means that the volume is constant. Using the kinetic theory of matter, which states that matter is made up of particles that are in a continuous state of random motion, we can see that this motion of particles is direct proportion to the energy. So now that the temperature of the tire has increased, it means the energy content has gone high. Therefore, the particles begin to move with greater average kinetic energy. They collide with each other more often, and they also collide with the containers, the walls of the container much more often and with greater forces, leading to increase in the pressure. That is how we can use the kinetic theory to explain this situation. Let's move on to question 10. Question 10 reads, the figure 10.1 shows part of a cathode ray oscilloscope in which cathode rays are produced. Okay, the diagram is there, viewers. Now they're asking us to say, explain why the filament emits electrons and explain how the electrons are made to move at high speed. The filament emits electrons. We must answer this first question, why? The filament emits electrons because it's been heated. And once you heat this filament, the electrons that are there begin to move and vibrate at greater velocities, average velocities. And so what will happen is that the vibrational motion will increase to the extent where the forces that were attracting these electrons to the filament will be defeated, and hence the electrons begin to evaporate from the surface of the filament. And these electrons are made to move at high speed by the presence of the anode voltage. The anode voltage attracts the electrons towards it very, very quickly and at a very high speed. So basically the anodes are there to accelerate these particular electrons. Part B. Describe an experiment to show that cathode rays are not electromagnetic radiation. Dear viewers, the question here is asking us to make sure that we understand what cathode rays are and what electromagnetic radiation is. Cathode rays are fast-moving electrically charged particles, which are in this case electrons. These are very fast-moving electrons, and they constitute cathode rays. Now, they are different from electromagnetic radiation in that electromagnetic radiation is energy that results from particles. Probably, for example, if an atom or, for example, an electron is going to move from a higher energy level to a lower energy level in an orbital, or in an orbit if you like, the energy can be released. So, I think we are going to say that here we are trying to differentiate between particles and energy. So, if we want to show that cathode rays are actually particles and not a form of energy, then we can probably we can probably that we do an experiment that is going to show that these are actually particles and not energy. One of them is to allow these electrons to move in an electrostatic field. I'll just draw it very quickly here. If we have a filament connected to a small voltage like 6 volts, and then it emits these electrons, we can let these electrons pass between two plates which are charged, you know, positive, and this is negative. What we can notice is that these cathode rays will be seen to be attracted towards the positive plate. This indicates that these are actually particles because they are changing direction. These are particles. That's one. Now, the other one we can do is to put on the way of these electrons a small light pedal, just a small light pedal, so that as these electrons move towards this, this pedal will be hit and it will begin to move, and when it begins to move, then it shows that actually these particles are actually particles and they carry kinetic energy, and this is the kinetic energy they are using in order to push this this pedal forward. So this shows that actually cathode rays are particles and not energy. But what results from there when these cathode rays, or if you like electrons, hit a target and they change direction, the kinetic energy they had may be converted now to energy, such as X-rays. That is how we can show these particular experiments. Part C. In each second, 8.0 times 10 to the power 14 electrons pass through the hole in the anode. The charge on an electron is 1.6 times 10 to the power minus 19 coulombs. Calculate the current in the electron beam. First of all, we must find the total charge that flows there by multiplying the number of electrons by the charge that each electron carries. 8.0 times 10 to the power 14 times 1.6 times 10 to the power minus 19. When we do this, what we realize is that we are likely to get 12.5 times 10 to the power minus 5. When we add this power plus this power, we are likely to get 10 to the power minus 5. These are the coulombs of charge. Now the question is not about coulombs of charge. They are saying calculate the current in the electron beam. So we say quantity of charge is equal to current times time. So therefore current should be equal to quantity of charge divided by time. The quantity of charge, we have it here. So it's 12.5 times 10 to the power of minus 5 divided by the time, and they're saying each second, and therefore we put 1 second here, so that we get 12.5 times 10 to the power minus 5 amps. That becomes the answer. We move on to question 11. A transistor is another kind of semiconductor. It is used to amplify current in a circuit. Draw the structure and the symbols of the transistor. Two things. Draw the structure and also draw the symbol for the transistor. So we start with the structure. We start with the structure. So this is the positive, we have N, and we have N, and we have the collector here, we have the base here, and we have the emitter here. That becomes the structure of a transistor. Then we move on. They are saying we must indicate also the symbol. All right, so we try and put up the symbol for the transistor. It goes this way, it goes that way, and then we draw something like this, and then we say this is the base, and we put an arrow here to show the direction of conventional current, and then we say this is the collector, this is the emitter, and that is the base. That is the symbol. So this is the structure, this is the symbol. Right. Now they are saying the figure below shows a transistor switch in a circuit. That is the circuit, dear viewers. The question says, copy and complete the complete circuit above by placing in a transistor in the correct position. So when we look at that, we see that it is in this way roughly. We have plus 9 volts there, and we have this going through the bulb, and all right. Then we have, just roughly, we have okay, we have a protective resistor here, and so we are going to put the symbol for the transistor here. We are going to put the symbol for the transistor there, and we draw this transistor, and we put collector, we put the base, and then we put the emitter, and then this can go to 0, which is negative, if you like, and then this will come this way. That is the diagram that we were given. There is a protective resistor here, and a transistor there, and this is about the circuit that they need for the first 2 marks that they want. Then they are saying, using the completed circuit of the figure above, describe how the transistor operates as a switch. Wow. When we look at this diagram, viewers, we see that V here is 0. As long as V is 0, the transistor operates such that the collector emitter current is larger all the time, larger than the current that passes through the base. So it operates on the principle that some small voltage must pass through the base, and then when it passes through the base, it triggers the path that is between the collector and the emitter to allow the larger current to flow. As long as the base current, the small current that is supposed to come to the base, has not come, then the transistor will not switch on. So in this particular case, therefore, we expect that V must grow, the V which is equal to 0 must grow to something like V equal to maybe 0.7 volts. If it grows only up to that much, then we see now electrons begin to flow in this pattern. I'm showing the electron current, how electrons are flowing. They are flowing like that. They are also flowing like that. And within here we have a forward bias of electrons within the transistor, and the electrons are flowing like that. These are electrons. As soon as electrons begin to flow like that, then now conventional current, please understand this. I'm talking about two things here, the electron current and the conventional current. The direction of the electron current is different, is opposite to the direction of the conventional current. Actually, the electrons, when they are moving from left to right, conventional current goes into the opposite. So in this particular case, once this PD across these 2 points grows to about 0.7 volts, we are going to notice a small current which is going to pass and go to the base of the transistor. And this is the base current that will trigger the collector and emitter current, which is larger. And this is going to be larger, maybe multiplied by 100 times or so, if you like. And then this is the current that will flow in this direction, the conventional current. When it flows like that, then the bulb will light. And then that way the transistor will switch on that particular circuit as may be needed. So that is how a transistor operates as a switch. It waits for the base current to arrive on the base. When the base current has come, then now it triggers the flow of current from the collector to the emitter, and hence the bulb lights. That is the way the transistor operates as a switch. Question 12. In an experiment to determine the half-life of radon-220 with a symbol shown, the following results were obtained as shown in the table below after allowing for the background count. All right. Part A, part 1. What is the origin of the background count? The background count comes from the background radiation, and this is coming from the environment, from rocks, and all of us seated here, viewers, even yourselves, you are experiencing this background radiation because it is coming from the surroundings, from the rocks, and people are exploding these rocks all the time, and so radiation is coming from there, and we are absorbing this radiation on a daily basis. Other than that, we can also experience background radiation from cosmic rays that are probably escaping from space. And so if those cosmic rays escape and they reach us, then we are likely to register background radiation. The question says again, how is the background count determined? It is basically simply by getting a GM tube with a rate meter on it. You bring it where the radiation is suspected to be coming from, and it will register this reading. Even before you bring the source that you want to deal with, the rate meter will show a reading on the GM tube, and that will indicate the background radiation. And you take note of that one, so that as soon as you expose the new and fresh sample to the GM tube, the rate meter will register now a higher reading, and then you subtract what was there before, which is the background radiation. That's how the background radiation can be determined. Part B. By plotting the graph of count rate vertically against the time horizontally, determining the half-life of radon, show clearly on your graph how you obtain your answer. Viewers, I may not be able to plot exactly on the actual graph paper now, but I'll try and explain it very quickly. Let me draw something to explain this situation. If we plot very quickly, we say count rate per second, and time in seconds. After we have plotted these figures properly, and using a good scale and we plot them properly, what we are going to notice basically is that we will have figures here. We will have figures here, like for example, the starting is 30, and so we might have maybe 0, 5, or maybe 0, 10, 20, 30, and so on. But supposing, just for argument's sake, we have a situation where we are starting with 30, okay, at time 0. So what we'll do is, we have these times like 10, 20, 30, up to, we have about 72, for example. So after we have plotted these correctly, we are going to generate an exponential curve, which will look like this. And take note that after you have plotted these figures these figures in the table on question 12, after you have plotted, you are likely to get this particular graph, and it should never and never touch the x-axis. Never. That is point number 1. Then number 2, as you work out the half-life from here, you must check out for half of 30. Come here and check on half of 30, which will be 15, and then you follow this graph up to there, come down with it, and take note of this time. That's not enough. You will have to go again and say half of 15, which is 7.5. Come here and find 7.5. Go with it. Come and see. Here, you are going to have another T2. These are 2 half-lives that you are going to get. So, T1 plus T2 divided by 2 is likely to give you the half-life of this sample. But mind you, from here to here, you take note of this. Then here, it's from this distance to here, you must subtract these 2 in order to get T2. So when you get this and you divide by 2, you are likely to get the half-life. In this case, half of 30 will be 15. Somewhere here, between 16 and 14. Between 16 and 14 here, you are going to get 15. And therefore, it means that half-life will be in between 50 and 60. That will be the answer, about 55 or so seconds. That will be the half-life. That's how we use this graph to determine the half-life. Dear viewers, I'm very happy that you've been with us. And so we are going to go on a short break so that as soon as we come back, we continue with the other questions that we have. Thank you so much. I can see a few people there. Thank you so much. What name is that now? Let me know those people commenting there. There is Mano Kangwa. Thank you so much for having been with us and following this program. Sorry? Ben. Okay, Muzo, we thank you so much for being with us. We hope that you can invite your friends also to join us. So we thank you so much. There's also Emmanuel. Emmanuel Kangwa, thank you so much. Please join us after the break.
I told the bus driver that I work hard for my money, so it better gets to Chipata.
Yeah, that's right. That's what I told him.
Yeah.
Weather, drama is no. Only Zambili.
Tituma. And he kept trying to tell us something, but I was like, Ukagamba, Tilo.
Cause cash money yeve across Zambia.
Tituma. Ati? At Basi and Kuchpat. The end of South Africa. Hello, what?
Run, K-Stop, run! Don't catch the bus.
Sending money doesn't have to be this dramatic. Open an MTN mobile money account today and send money to friends and loved ones across Zambia instantly. Dial *303# to send money with MTN, Zambia's #1 network. with MTN Mobile Money. Tituma.
MTN. Everywhere you go.
Rise up this morning, smile with the rising sun. Three little birds pitch by my doorstep, singing sweet songs of melodies pure and true, saying, this is my message to you. Singing, don't worry about a thing, 'cause every little thing is gonna be alright. Singing, don't worry about a thing, 'cause every little thing is gonna be alright. Cause every little thing is gonna be alright.
How you use your data is up to you. With the widest network coverage, it's amazing what you can do on MTN.
This is my message to you.
Welcome back, viewers, to this MTN Teleschool, and we thank you for being with us. We proceed with some of the questions that are from the same paper, but from question 5 to question 8, 2016. We begin. Elena poured 100 cubic centimeters of water in beaker S and 100 cubic centimeters of water in beaker T. Beaker S was kept at 40 degrees and beaker T was kept at 80 degrees in the same part of the room. The figure shows the two beakers after 3 days. So the diagrams there show exactly those two beakers. Part A, part 1 of the question. Explain why more water evaporates when the water is kept at 80 degrees. Again, this takes us to the kinetic theory of matter, where particles tend to move faster when they have energy, and it says that all matter is made up of particles that are in a continuous state of random motion. But what is happening here basically is that the particles that have so much energy sufficient to allow them to escape from the forces of attraction on the surface of the vessels, they tend to jump into the air via the process of evaporation, because they've managed to defeat the forces of attraction, and therefore they tend to move much quicker and much faster when temperatures are very high, because they have energy. So that's the reason when water is kept at 80 degrees, more evaporation takes place. Part 2, apart from an increase in temperature, state one change that causes water to evaporate faster. We must quickly think that the larger the surface area, the more the evaporation, the presence of the wind. And so if wind is blowing so much, it means that the environment above the beakers will be thirsty of the water vapor. So more vapor will join in the air. We must also think that if the surface, the space above the beakers is saturated with vapor, maybe it's too humid, then the evaporation becomes low. Part B. Question 5, Part B. The following information was collected and recorded during an experiment to determine the specific heat capacity of water. Heater rating 60 watts. Voltage 12 volts. Mass of water 200 grams. Initial temperature is 20 degrees C. Final temperature is 48.2 degrees C. And time taken, time is 10 minutes, which is equal to 10 times 60 seconds, so that we get 600 seconds. So that is the information that we have on this question. We move on to the question. Calculate the specific heat capacity of water from the data. All right. The quantity of heat supplied should be equal to MC delta T, where delta T is T final minus T initial. In this case, this is going to be 48.2 minus 20, which will be 28.2 degrees. That is the change in temperature. Okay, so the change is 28.2 degrees. Okay, so then now we can say that M is 200, and the quantity of energy spent there is power times time, and this is C, and the change in the temperature is 28.2. So power times time is 60 times 600, which will be equal to 200 C by 28.2. When we do that, what we see is 36,000 equal to 200 C by 28.2. Okay, so when we cancel out these two zeros, we get 360 equal to 2C times 28.2. So we are going to find that 360 is equal to 56.4 C, and then we divide by 56.4, then we are likely to get 6.383 joules per gram per degree C. Okay. Or if we convert 200 grams to be equal to 0.2 kg, then we will get C as 6,383.8 joules per kg per degree C. We move on to question, the same question 5 part 2. To the 200 grams of water at 48.2, 100 grams of cold water at 20 degrees C was added. Calculate the final temperature of the water. Okay, let the final temperature be TF. Okay, so that the change in temperature for the hot water will be TF, I beg your pardon, will be 48.2 minus TF. And then the change in the temperature of the cold water will be, change in temperature of the cold water will be TF, which will be bigger, obviously, minus 20. So the meaning here is that energy that will be lost by the hot water will be the energy that will be gained by the cold water. Okay, so we can now say that energy lost is equal to energy gained. Okay, so the energy lost is M hot times C and times change in the temperature of the hot, which should be equal to M cold times C times the change in the temperature of the cold. So now that means that mass of the hot water is 200 times C times the change in this temperature, which is 48.2 minus TF. That should be equal to mass of the cold, which is 100 grams, times C times change in the temperature of the cold water. Okay, so when we do that, what we realize is that the specific heat capacity for water is the same both sides, so we can cancel out this. And then at the same time, we can also say 100 grams cancelled, 100 here, we find 2. So what we notice is that we have now 96.4 minus twice TF. That should be equal to TF minus 20. I hope people are following. When we do that and we collect like terms, we see 96.4 plus 20, that should be equal to TF plus twice TF. Meaning when we again superimpose this particular equation, we say that the ones that are on the right, for example here, the things that are on the left are equal to the things that are on the right. So even when we swap them, things should be okay. So we say 3TF, that should be equal to 96.4 plus 20, which is 116.4. Then that gives us TF as T final as 38.8 degrees C. That is the answer. That is the final temperature of the mixture. Right? Question 6. Dear viewers, Elena wrote the information in the figure in her notebook. That's what we are told. And started with gamma rays, X-rays, ultrasound, microwaves, infrared, and radio waves, increasing wavelength as shown. Now the question says, list 2 errors in the learner's notes. Very quickly we notice that there is a problem with what has been put just after X-rays. It shouldn't be ultrasound. It should be ultraviolet. That is the first error. It should be ultraviolet. And then you notice that other than that mistake, as soon as ultraviolet is put there, the next thing should be visible light. After visible light, that's when infrared must come. And then now after infrared, that's when microwaves must come. So microwaves must come in between infrared and radio waves. So that we end with radio waves. Those are the errors that were made by that student. So you can choose any 2 of those to generate what the answer requires. Part B, state and explain an application of X-rays in engineering. So we have medical engineering, we have other engineering fields. So we can choose which engineering we want to derive these answers from. But by and large, you notice that X-rays can be used to detect small cracks in metals. That's one. We can also use X-rays to check if something has been welded properly or not. We can also use X-rays to check if a certain metallic material has been properly manufactured, like the hot plates on our stoves. If we want to know that the element inside is properly and is uniformly made, we can insert X-rays. We can pass X-rays through there. The image will come out to show us where the faulty manufacturing issue is. If there's a fault there, it means that that hot plate may not last much. But if there's uniformity in the manner that hot element inside is manufactured, then we should know that it will last for a longer period of time. So those are some of the uses for X-rays. Other than that, in the medical engineering field, you can use X-rays to generate X-ray photographs for broken bones. If footballers are playing and then he injures himself or she injures herself, then they can take a picture of that situation. X-rays will pass through flesh very easily and fail to pass through the bones very easily. So it will create shadows where the bones, the joints of the bones are. So those shadows will tell us exactly how the bone has been dislocated or things like that. I think those are the ways in which in the medical field these X-rays can be used. Other than that, they can detect, they can treat cancer using X-rays, a few dosages of X-rays. Excess of it can generate big problems in terms of mutation. Dear viewers, I think some of those are the uses for X-rays. We move on to question 7. The figure shows a solenoid made from wire wound around a plastic cylinder. So we have that situation there. Let me just quickly draw the cylinder very quickly, just roughly for our understanding. This is our cylinder. So we are told this is positive and it is going this way and then coming out and then coming out and you can see that if we check here conventional current is what is very important, viewers. Conventional current will always move from positive to negative. So you must indicate it on your diagram the way I'm indicating it here. And then when you do that, you find that conventional current is flowing like that. So what you can do, two things here. One, you can come this side and view the way current is flowing around this solenoid. Come this side, put your eye this side and see how current is flowing this side. Is it flowing clockwise or anti-clockwise? Like in our case here, we see that it's flowing clockwise in this direction. So where it's flowing clockwise, you put south. And then the other side, it will be flowing anti-clockwise, you put north. So the magnetic field that is generated as a result of this current passing around this solenoid is as shown. And it's going to generate a magnetic field, of course generating field lines inside and outside the cylinder. So the question says, a current in the solenoid produces a magnetic field, which is okay. On the figure, draw the pattern of the magnetic field lines inside and outside the cylinder. So inside the cylinder, magnetic fields will run from north to south. So I'll put these magnetic field lines like this so that you see that they are moving from north to south. Okay? And then we are told even outside we must show. So we are going to show like this. I beg your pardon. Right. I must join properly my. All right. So they will move like this. Like this. So that is the direction of the magnetic field. So you can see that I've drawn two fields here. Some are inside and then some are outside. So that's the way we must show. We are through with that particular part. The figure shows a beam of beta particles in a vacuum passing into a magnetic field. Okay. The movement of beta particles from left to right is an electric current. Okay. Question B, part 1. On the figure, draw an arrow to show the direction of conventional current. I've just been saying this all the time. I'm saying that if electrons are moving from A to B, then that is the electron current. The conventional current moves from B to A, opposite to the direction of where the direction of the electron current. So when electrons are moving from A to B, conventional current moves from B to C. So we quickly go on the diagram and then draw the direction of, so this is the field out of paper, and the electrons are moving this way. All right, these are electrons that have been shown here. So it means conventional current is going this way. Conventional current is going this way, opposite to the electron movement. Okay. Part 2. The direction of current in the solenoid is reversed. State what happens to the path of the beta particles. They also change direction. If they're going to go upwards, then in that particular case, they will actually go down. Like they are going out of the paper now, the fuse is going out of the paper, so it was supposed to be going upwards. Now it will come down like that. These are the the directions of the beta particles. Opposite to where they were going at first. Dear viewers, that's the end of that question. We move on to question 8. The figure 8.1 shows a thundercloud with a flat, positively charged base as it passes over a tall tree standing in a flat open land. So we have a cloud there which is going to pass near that tree and of course many other objects down there. So they are saying that on the figure, mark the charge on the tree. We must understand that right away the charge will be negative on the tree. So on the tree that I've drawn here, I will put negative. That is the charge on the tree. I hope viewers are able to see what I've done here. And let me just quickly remove this. Let me just remove this and say that we have this cloud which is positively charged. Okay, all right. Okay. Explain how the tree becomes charged. So what it is that we must understand that in the space there are charges there. And these charges are going to be attracted. And like in our case here, what is going to happen is that all the positive charges that are in space are going to be repelled by the negative cloud to the ground. We must not just be focusing on electrons all the time when we are discussing these charges. No. We have charged the ions in the air as a result of colliding, you know, air molecules colliding with each other and other radiations, you know, knocking off outermost electrons from atoms and causing ionization. So we also have in the soil positive and negative charges in terms of ions and so on. All of these ions must be considered. So these are the ions that are going to be repelled by the positively charged cloud. They will be repelled because they are positive also. So the negatively charged particles will be attracted to a tree. That's the reason the tree will remain negatively charged. The other similar charges will be repelled to the earth. That's the reason the tree becomes charged in that manner. Okay, part B, a lightning strike occurs and in 2.0 times 10 to the power 4 minus 4 seconds, a charge of 560 coulombs passes from the cloud to the tree. The size of the charge on an electron is 1.6 times 10 to the power minus 19 coulombs. Calculate the number of electrons that pass between the tree and the cloud. Dear viewers, we go quickly to these calculations and say that, okay, number of electrons will be equal to total charge. No, I beg your pardon. Let me write properly this. Total charge divided by the charge for one. Charge for one electron. So we are going to get 560 divided by 1.6 times 10 to the power minus 19. So we are going to see 560 divided by 1.6 times 10 to the power 19. Because 19 will come on top and be positive. So 560 divided by 1.6. We are going to probably get, let's say, 350 times 10 to the power 19, so that we get 3.50 times 10 to the power 21. Okay, so these are the number of electrons. Calculate the average current in the lightning strike. All right. Quantity of charge is equal to IT. I is quantity of charge divided by T. We know the quantity of charge, it is 560. And then we know the time, it is 2.0 times 10 to the power minus 4 seconds. So we are going to say 560 divided by 2.0 times 10 to the power of 4, because the power will come on top and be positive. So that we get 280 times 10 to the power 4. That means 2.80 times 10 to the power of 6 amps. That is the current that will flow. Dear viewers, we've come to the end of the paper. I thank you for following us closely. I thank all of you that have been with us. I thank all of you, and again, my name's James Kabuye. We are happy that you've been with us on this telescope till now. Thank you so much. See you in the next episode. Yellow.
Oh, tiende pamoja ni mtima umo, 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 tiende pamoja